Example problem 7 reads, what is a gas's temperature in Celsius when it has a volume of 2.5 times 10 to the minus 2 milliliters, 203 moles, and a pressure of 143.5 atm? So the first thing that should catch your attention when you're reading this problem is the word moles. And so since the word moles is there, we know we're not using the combined gas law equation. We know instead that we're using PV equals nRT. So the problem asks us right off the bat for the temperature. So we know that's the variable that we're going to be looking for. It says that the volume is 2.5 times 10 to the minus 2 milliliters. It says that N equals 203 moles. It says that pressure equals 143.5 atm. And no matter what, R is always going to equal 0.0821 atm liters divided by moles Kelvin. There is another gas law constant, but we are not going to use it in this class. I prefer that you guys use this version of the gas law constant. So the only thing that needs to be converted in this problem is going to be volume. We need to convert milliliters to liters. So draw your multiplication symbol, draw your division bar, bring milliliters down, and then determine whether it is a one-step or a two-step conversion. So we're going from something with a prefix to a base unit, which makes that a one-step conversion. So you give the 1 to the thing with the prefix, which is milli, and the metric system constant for milli to the base unit. And so the metric system constant for milli is 1 times 10 to the minus third. So milliliters cancels and you're left in liters. So in your calculator, you should write 2.5 times 10 to the minus 2 times 1 times 10 to the minus 3. And that will equal 2.5 times 10 to the minus 5 liters. So now we're ready to put everything into the ideal gas law equation. So our P is 143 atm. Our new V is 2.5 times 10 to the minus 5 liters equals N is 203 moles. That is a lot of moles. R, the ideal gas constant, so 0.0821 liters atm divided by moles Kelvin. And then T is our X, or you can put T there if you'd like. Either way, it's correct. So we're going to treat everything right here as one variable. So we're going to divide by 203 moles and 0.0821 atm liters divided by moles Kelvin to get X by itself. So this is all going to cancel and X is going to be by itself. So we're going to go ahead and divide by 203 moles and the gas law constant 0.0821 liters atm moles and Kelvin. And so you're more than welcome to put this all in your calculator at one time, but I'm going to do it in 2 separate steps. If you decide to do it all at once, make sure that you do double parentheses here and here. Do your division sign and then double parentheses here and here to make sure that you're separating that numerator from the denominator in that calculator. So the top 143 times 2.5 times 10 to the minus 5 equals 0.00357. So we'll say 0.0036. So 0.0036. And I'm actually going to move that over further because we have some more conversions to do at the end. So 0.0036. And so the units don't go anywhere because when you multiply ATM by liters, it becomes an ATM liter. They don't cancel out. And so the denominator, 203 times 0.0821 equals 16.666, so we'll say 16.67. And so the units are a bit odd on this one, so moles will cancel, and the only thing that will come down is going to be liters, ATM, and Kelvin. And so you can see here in the final calculations where ATM cancel and where liters cancel, and you're left in Kelvin, which is appropriate for temperature. So in your calculator, 0.0036 divided by 16.67 is going to give us a final temperature of 2.159, so 2.16 times 10 to the minus 4 Kelvin. But they're not interested in Kelvin, they're interested in Celsius. So whenever we turn a temperature from Celsius to Kelvin, we add 273.15. So to do the opposite, we have to subtract 273.15. So minus 273.15. And I think I have a slide somewhere in this PowerPoint where I break down the temperature conversions. Going a little bit further back, maybe into Charles's law. Yeah, here they are. So temperature in Kelvin minus 273.15, and that's how you're going to convert that to Celsius if you have to, which in this particular problem we do. So in our calculators, we're going to put 2.16 second E to the minus 4 minus 273.15. And it's okay to get a negative number in Celsius. It's okay to have a negative temperature. It's just really cold, right? So minus 273.149, so we'll say 0.15 degrees Celsius, and that is our final temperature in degrees Celsius. So let me know if you have any questions about example problem 7.